Hi everybody, so this video is going to be all about Unit 1, Lesson 10, which is about a new idea we're calling continuity. So we have several learning targets for today. The first is I can identify where a function is discontinuous. So this is going to be a new vocabulary word for us. We're going to need to talk about what it means and then identify where that happens. The second learning target is I can classify discontinuities of functions. So discontinuities fall into different categories. We're going to classify them. I can apply the definition of continuity to determine whether a function is continuous at a given point. So in order to apply the definition, we're going to need to start by learning the definition of continuity and then use it to determine whether a function is continuous or not at a certain point. And I can justify whether a function is or is not continuous using the definition of continuity. So again, we're going to be justifying our answers in today's video, so explaining our thinking about whether a function is or is not continuous using the definition. So again, learning the definition is going to be important. It's going to help us with two things. We can determine whether it's continuous or not and use it to justify our answer. And last but not least, I can determine the intervals, so sections over which a function is continuous. So these other learning targets were kind of about discontinuities. I can figure out where I'm discontinuous or classify the discontinuities. And now we're going to also look at where we are continuous. So let's start with just what does it mean to be continuous? While limits told us where a function intended to go, continuity guarantees that the function actually made it there. So if we were to look at this graph, we would know that the limit exists at x equals 1 because both the left side and the right side of the graph approach the same value when x is close to the value of 1. However, one thing that was kind of different is that it didn't matter for limits whether this was an open or a closed circle, whereas we were used to that kind of being important from previous math classes. Today, we're going to be talking about continuous. Now, I like to think about continuous meaning connected. And by contrast, discontinuous or a discontinuity would be disconnected. So whereas for a limit, it doesn't matter whether that's an open or a closed circle. For continuous, now we're going to see if that's filled in or not. This function would be considered continuous because the limits approach the same value, and when you get there, it's actually filled in, it's connected. Now, there are three parts to the definition of continuity. In order for a function to be continuous, it must meet three conditions. First, and it's kind of like three things that have to be equal. The limit as x approaches your value, whatever that might be, of f of x from the left must be equal to the limit as x approaches your value from the right. And both of those things now must be equal to the actual function value. Now, if we think about how this is different from a limit, for a limit, we only care about the first two things. Does the limit on the left equal the limit on the right? That's what makes a two-sided limit work. So this first part of the definition of continuity is just to determine whether the two-sided limit exists or does not. What makes continuity different from just a limit is that answer, our two-sided limit, must be equal to the function value. Or on a graph, it's the location of the closed circle. So let's go ahead and start thinking about continuity. In order to think about continuity, it's actually easiest to think about discontinuities. So in general, we assume a function is continuous. Everything is connected unless we see one of these three problems. If a function is not continuous at a specific number, we say that it has a discontinuity at that x value. So not continuous. We don't say not continuous, we say it's discontinuous or it has a discontinuity. These discontinuities fall into two categories. There's removable and non-removable. Within removable, we just have holes. This means the two-sided limit exists. So if we look at this graph, there's a hole in the graph. The two-sided limit exists, but when you get there, it's an open circle. On this graph, there's a two-sided limit that exists, but when you get there, there's an open circle. So a hole or a removable discontinuity, the two-sided limit exists. Now there could be, for example, a closed circle somewhere else, kind of like that. That is still considered a removable discontinuity or a hole in the graph. Now, non-removable discontinuities, there are two types. There's a jump and there's infinite. A jump is when the one-sided limits have different values. So for example, if we check the limit from the left and the limit from the right here, there are two different points that we're approaching, so the limits would have two different values. The same thing on this graph. The limit from the left and the limit from the right do not agree. They have different values, and it doesn't matter whether they're open or closed circles. It's called a jump because your graph is jumping from one limit to another limit. The second type of non-removable discontinuity is what's called infinite. An infinite means at least one of the one-sided limits is infinite. So if we look at this graph, the one-sided limit here would be positive infinity, and the one-sided limit here would be negative infinity. On this graph, one of the one-sided limits approaches a number, 2, but the other one-sided limit approaches negative infinity, which means it's still an infinite discontinuity. So here's what we're going to ask you to do with this information. We're going to be asked to locate and classify discontinuities. So look at the graph, tell me where it's not connected, and classify them using the vocabulary in the table above. For each discontinuity, use the three-part definition to explain why it's not continuous. So is it because the limit, so going back to the three-part definition, is it because the limit from the left does not equal the limit from the right? Or is it because the limit from the left does not equal the function value? Like, what's the reason why this definition is broken? Then finally, we're going to look at the intervals over which our function is continuous. So let's just start on the graph with locating the discontinuities. Before I write anything down, I'm just going to figure out where does the graph disconnect. The first place the graph disconnects is at -1. You can see that the left side and the right side are not connected there. The second place would be in the middle here at x equals 0, and the last place would be at x equals 1. So that tells me that there should be three things I'm listing under my discontinuities. The first thing I'm going to list is x equals -1. Now I'm going to classify it. So locate, then classify. So if I were to classify this discontinuity, I would call this a jump. And the reason I would call this a jump is because the two one-sided limits have different values. It jumps from one point to the other one. So I would call this a jump. And if I want to use the three-part definition to explain why the function is not continuous, I would say the limit as x approaches -1 from the left is not equal to the limit as x approaches -1 from the right of f of x. The two one-sided limits are not the same. The next x value I'm going to look at is 0. Now I'm going to classify this as an infinite discontinuity. And the reason I would classify this as infinite is that the left side seems to be going up towards positive infinity. So what is the reason that I would give using limits? There are lots of different reasons here. I could say the limit from the left is not the same as the limit from the right. I could say that the limit from the left is infinity. I could say that it doesn't match the function value. It doesn't really matter as long as you state one of the correct reasons why this is discontinuous. So I could say the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. I could also say that this doesn't equal the function value at 0 because there is no function value at 0. There's no closed circle. Finally, I'm going to look at what's happening when x is approaching 1. At x equals 1, you can see that the two one-sided limits are the same. They both approach this open circle. However, the closed circle is somewhere else. That is what's called a removable discontinuity or a hole in the graph. And my reason would be that the limit as x approaches 1 from the left and 1 from the right is not equal to the function value. Now, to avoid having to write the left and the right separately, in this case, because they're actually the same, I would say the limit as x approaches 1, which exists and is the same on both sides, is not equal to the function value at 1. So the closed circle is somewhere else. Last but not least, we're going to be asked to list the intervals of continuity. Now, intervals of continuity means, okay, if this is where the graph is broken, then where is it okay? So my first interval would be this section of the graph, right here. If we think about it in terms of the x values, it's all of the x values from -infinity to -1. And because this part of the graph has a closed circle here, I would use a bracket instead of a parentheses. The next section of the graph would be in between -1 and 0. And because there's an open circle here and an asymptote here, I would use open parentheses for both. Next, I would go from 0 to 1. And because there's an open circle and an open circle, I would use parentheses for both. And last but not least, the last section of the x values is from 1 to infinity. So those are my intervals of continuity. In other words, I'm disconnected at -1, 0, and 1. I'm connected everywhere else. And you'll notice that the places where these intervals break apart are -1, 0, and 1, because those were the discontinuities. Now, what if we wanted to do this without a graph? Discontinuities are most likely to occur in rational functions and piecewise functions. So, when are you going to be likely to find a whole discontinuity or removable? You might find this in a rational function. If a factor cancels from both the numerator and the denominator of a rational function, you're going to have a whole, which is a removable discontinuity. In order to determine this, I would just factor the numerator and the denominator, which in this case would be x plus 2 times x plus 3. So because this factor cancels in both the numerator and the denominator, we would say that there's a removable discontinuity at x equals -2. And if you wanted to justify that using limits, because it's removable, because it's a whole, both the left and the right will agree, but the function value will be elsewhere. So you would say that the limit as x approaches -2, and I'm using a two-sided limit here because the left and the right will agree for a whole. If you kind of imagine it in your head, it looks like this. But we're not going to be equal to the function value there. Another time that you're very likely to have a whole or a removable discontinuity is if there's a piecewise function. So for a piecewise function, we would need to check the limit of both sides of the breaking point to see if they have the same y value, but then maybe the function value is located somewhere else. So in order to figure this out, we're going to notice that this top part of this piecewise function is valid for all of the x's that are not 2, and the bottom is valid for all the x's that are 2. So to check the limit as x approaches 2 from the left, I would use the bottom part of this piecewise function. I would use the top part of this piecewise function because 2 from the left is not 2. It's close, but it's not 2. And if I were to plug that in, I would get 4 minus 5, which is -1. To check the limit as x approaches 2 from the right, I would do the same thing. I would use it's not 2, we're just close to 2, and I would get -1 again. To find the function value, that's where I use this middle part of the limit here. So this is just for the function value. In other words, f of 2 is equal to 7, which is not the same as these two limits. So that's how you know that there's a hole. The left and the right agree, but the function value is somewhere else. We're going to have an infinite discontinuity, which is non-removable, or it's called an asymptote, usually when there's a rational function. If a factor does not cancel from both the top and the bottom, then you're going to have an infinite discontinuity. So if I were to factor here, I would have x plus 2 divided by x plus 2 times x plus 3. We saw in the example up here the x plus 2 is canceled, but that means there's still this x plus 3 here. That's going to tell me that there's an infinite discontinuity. At x equals negative 3. Now, because of that, I could look at the limit on both sides. So I could say, what is the limit as x approaches negative 3 from the left? Which, if I imagine plugging in a number slightly to the left of negative 3, that would be 1 over negative 3.1 plus 3, which is 1 over negative 0.1, which is negative infinity. I could also examine the limit from the right, which in this case would give me positive infinity. And since those do not agree, my limit does not exist. I could also just say that it does not equal f of negative 3 because f of negative 3 is undefined. It doesn't exist because there's an asymptote. Last but not least, we can have a jump discontinuity when there's a piecewise function. If the limit on both sides of the breaking point do not have the same y value, then you have a jump. So the difference here is that for this one, the limit on both sides was the same, but the function value was somewhere else. That's going to be removable. Here, if the limit on both sides is different, that's going to be a jump. So to check the limit as x approaches negative 1 from the left, we're going to use the top function here, which would be 0. And to check the limit as x approaches negative 1 from the right, we're going to use the bottom function here, which would be negative 1.5. Since those do not agree, we would end up with a jump discontinuity. So, what am I going to ask you to do with this? Well, let's say I ask you to find the values of x where the function is discontinuous and describe the type of discontinuity and justify your answer using the definition. So the first thing you want to do is just kind of decide what kind of discontinuity there's going to be. Based on the function in number 1, I can tell that there's going to be an infinite discontinuity at x equals 3, because that is a factor that does not cancel from the numerator and the denominator. So I've found the x value and I've classified it as infinite. What I'm going to do next is use limits to explain why. If I were to find the limit as x approaches 3 from the left, then I'm going to plug in a number slightly to the left of 3, which is 2.9, which gives me 1 over a very small negative number, which is going to be negative infinity. If I were to find the limit as x approaches 3 from the right, I would plug in a number slightly bigger than 3, like 3.1, which is going to give me a positive small number, which is going to be positive infinity. Therefore, the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right of f of x. And that's how you use the definition. The limit has to equal the limit has to equal the function value in order to justify your answer. For problem number 2, it's a piecewise function. So I know the breaking point is what I'm really worried about here. So the first thing I'm going to do is I'm going to try to just sort of, without doing a whole lot of work, determine if this is a jump or if this is going to be removable. So if I check the limit as x approaches 0 from the left, I'm going to use the top function here, which means I get negative 7 over 2. And if I check the limit as x approaches 0 from the right, I'm going to get negative 2. Because these two limits are not the same, I'm going to say that there's a jump discontinuity at x equals 0 because the limit as x approaches 0 from the left of g of x is not equal to the limit as x approaches 0 from the right for g of x. All right, thank you guys so much for watching. This was our introduction to continuity, and I hope I will see you soon.